Hello everyone, welcome back to my channel. Today I'm going to talk about the size and shape optimization of truss structure by using the Python code with the particle swarm optimization algorithm. So first I want to show you the benchmark problem that I'm going to solve in this video, and you can check this paper in the link in the description. So this is the benchmark problem that we're going to solve, and I already completed the Python code for the size and shape optimization, but I will explain it step by step how this code works. And you can read this paper for more information, and you can check in table number 2 and number 3 here. So we have a 15 bar planar truss structure, and in this example we have two types of variables. So we have area variables and the geometry variables. So the idea of this optimization is to find the total weight of the truss structure with the minimal size and the best shape of this truss structure. So this is the result that we want to obtain. So as you could shown here in figure number 2, this is the optimal shape of the truss structure, and in the figure number 3 here, it is the convergence curve of the optimization solution. And for the area variable shall be selected from the list A here, and the geometry variable shall be within the limit as shown in this table, and we have the Young modulus E and material density rho. And if you look at the right side of this table, you can see the stress limit, which in this program it will be the design constraint, and we have only one design constraint in this problem. But we have 23 design variable. So we have here the size variable and the geometry variable, which includes x and y axis. And you can check the total weight in this table, and this is the result for the particle swarm optimization. And for the optimization algorithm of the particle swarm optimization here, it's only used 40,500 structural analysis. So in our code we will do the same in this paper. Okay, so first we start with the library. So we need the NumPy and the Matplotlib library so that we can plot the convergence curve and also the shape of the truss structure. And we need the truss structure parameter like Young modulus, the material density, and this is the stress limit. And next we need to input the node information and also the bar connectivity information as well. So this number here is the node number. So in this code the array start with 0, so it will be different in this. It will be different from the picture here. So the node number 1 in the Python code will be number 0, and the last node of the Truss structure will be number 7, while in this picture it is the node number 8. So please be careful with that also. And next I create a node original here to it actually the same value from this information here, but I want to create another variable because when we do the optimization, the node here will be replaced by the value from the geometry variable. So we need to keep the original value as well. And next we need to define the applied force. So in this case, the force applied to the node number 8 with number 8, and we import number 7 here because of the Python code, and the value is minus 10, and you can check the value here. And this is the degree of freedom condition, which also mean that we define the support for this structure. So we have two support which located at node number 1 and number 5. So the value here will be 0 and 4, and this is the size variable list. But we need to create another list which contain the index of this value. So I use the command linspace, and the value start from 0 to the length of array AI minus 1, and the number will be the length of array AI. And this type of array is the integer. So we need this variable in order to import in the optimization algorithm. And next we need to define the node condition. So this is the limit of the node can it can move. So we have for x2, x3, y2, y3, and so on. So we have information here. So this is basically the limit, or the lower bound and upper bound of the search space for the geometry variable. And I will skip this function for now. So next we can look at the Truss analysis function here. So this is the function that we defined in previous video. So you can check in my previous video to see how we can create the code for Truss structural analysis by using the direct stiffness analysis in this video, and I will leave the link in the description, so please check it out. And don't forget to check my previous video about the particle swarm optimization as well, so that you can have the fundamental knowledge about the particle swarm optimization. And here we need to adjust something a little bit. So the input here will be the design variable, which includes both size and shape variable. So we have to divide the size and shape variable from one another. So I create variable A here, which contain the size variable, and it will be take the value from the list AI here, and the index is from the input that we use here, and we need to call the assign geometry function. So this function is for set the coordinate of the node. So for each iteration of the optimization problem, the node or the geometry variable that we define, it will change every time, every iteration. So we need to assign the value that the geometry variable updated to the node array here in order to do this structural analysis. So that's why we need to create a function here called assign geometry to do that. And we have 10 coordinate that we need to assign. So we have for node number 2, number 6, number 3, and so on. So you can check the function here to see how it's work. Okay, next we need to return the stress and mass. So the variable mass here is the total weight of the truss structure, so we need to do the summation here. And next we can create a parameter for particle swarm optimization. So first we can start with the design variable. So in this case we have the size variable, which are also equal to the length of the array bars, and the shape variable or geometry variables, which equal to the length of the array NC that we define here. So the total value of the design variable will be equal to the summation of D1 and D2. And next we need to set the lower and upper bound of the search area. So this is the limit of the position for each particle, but we need to combine the size and shape limit. So the first line here is for the size variable, and the second line here is for the shape variable. So there are two columns. The first one is the minimum value, and the other one is the maximum value. And this line is for combine the limit from the node condition to the array H limit here. So the node condition we define in here. So all we need to do is combine it, but we need to combine it vertically. So we set the axis equal to 0. And next we can define the lower and upper bound of the velocity, and the size of this array will be the same as the array X lim here. So the value of the number of the row will be will be D, and the column is 2. So the first one is the minimum value, and the second one is the maximum value of the velocity. And next we can define the maximum value of iteration and total population. So the structural analysis in this paper equal to 4500, and it's also equal to the maximum number of iteration multiplied by the total population. So 9 multiplied by 500 will be equal to 4500 structural analysis. And C1, C2, and W is the acceleration constraint and the initial weight respectively. And you can check this information in my previous video that I just shown you. And you can also check my site optimization video as well. So the site optimization and the size and shape optimization will be is different from each other, because with combine both size and shape, the truss structure will be the optimization result will be better than the one with the size optimization only. So that's why we need to do both size and shape optimization of the truss structure. Okay, next we can set the limit of the velocity. So this is actually the same in my previous videos, so don't forget to check it out. And this is for the plot of the truss structure. So we need to import the node, and we need to set the value here, whether if you want to change the node from the original to the update one or not. So if it equal to 1, the function here will be call. So next week, okay, I will skip this first. We'll come back and explain this later. But now we can start the initial position and velocity of the algorithm. So I create several Python array here for position, velocity, and the fitness value or cost of the optimization, and the stress here for the design constraint. And for the size variable, we can select from the array A index, and for the initial position I want the value will selected randomly from the A index array, but the value shall be bigger than 15, because I want the value here, I want the section for the initial position to be a little bit big, so that the stress of each member be within the limit of the limit here. Okay, next we can define the node or the geometry variable. So it is selected anywhere within the limit of the geometry variables. And for the velocity, it is the same. So the value here will be selected anywhere randomly within the velocity limit. And then we can call the truss analysis function to do the structural analysis, and then we can obtain the stress and the total weight of the truss structure. Okay, next we can collect the data from the initial position. So we can create the personal best position, personal best cost, and we can also find the global best position and global best cost as well. So this is for initial calculation only, and we need these two variables to collect the data of the optimization. Okay, next we can start our first iteration of the optimization. So this is the velocity equation, and you can check the paper from the link in the description for the this equation also. And then we set the limit of the velocity by call the function limit v here, and then we update the position of the design variable for every particles of the population. And next we need to adjust the position a little bit, because when we do the summation here, the value will not be integer anymore, so we need to change it to integer from this list. So that's why we need to create a function here, and I call this find nearest. So this function will change the value, one value, and change with the value from the array, the input array here, and it will find the closest or the nearest value inside the array here and replace it to the current value. So this value will be updated, and it will become the integer value. So now after we change this value, we can run the structural analysis to find the stress and the total weight of the truss structure again. And this is for the design constraint, and you can check the design constraint in this paper. I leave the link in the description as well, so please check it. So this is how you can control the stress of the optimization. And next we can find the personal best position, the personal best fitness value, and then we can find the global best position, also the global best fitness value as well. And finally we can collect the data for every iteration. And next we can plot the result and also print the final value. So you can print the design variable, the stress, and also the total weight of the truss structure as well. So in this code I create two figures. So the first one is for the convergent curve of the of the optimization problem, and the other figure is for the original shape of the truss structure, and also the optimal shape from the algorithm in this code as well. So I'm going to run this code to show you the result. Okay, so this is the result of the optimization. So we have the convergence curve here, and you can compare with compare with the result in this paper. And this is the optimal shape that the algorithm obtained. So the shape here, of course, it will not be the same from this picture, because they use a different algorithm. And you look here, we have the design variable. So this is the area variable, and this is the geometry variables. And you can check the stress as well. So the stress is within the limit for each members, and this is the final value of the total weight of the truss structure. So you can compare with the result in this paper here. So the code here is bigger, but keep in mind that you have to run this optimization many times to find the best one. So you can run 20 times or 10 times to see which one is better, and you can compare with this paper. So this is how you can do the size and shape optimization together for the truss structure. I hope you get the idea from this video and apply it to your own project. And if you have any question, please comment in the this video. So that's it, and I see you guys in my next video. Thank you for watching.